Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This is the second video in a planned playlist on statistical tests. It is called T-Tests, Part 2 of 2, Calculations and Analysis. You can see the others in this playlist that I have completed or that I plan to do. There's a Part 1 video on t-tests, 3 videos on the chi-square tests, and 1 on non-parametric tests. The F-test is already covered in the video F, the test statistics and its distributions, which is in the playlist on distributions. If you're not familiar with the test statistic T, you may want to view my video T, the test statistics and its distributions, before viewing this video. I also have a video on Z as a test statistic. See statisticsfromatoz.com/videos for the latest status of my videos, completed or planned. As usual in the book and in these videos, we'll start by going quickly through a list of keys to understanding, or KTUs. This will give you the overall picture of the concept on a single page. And then we'll go into detailed explanations of each of the keys. For this video, there are 6 KTUs. The first key to understanding tells us that much the same thing happens in the 3 types of t-tests covered in Part 1. There are just different formulas for t and for the degrees of freedom, df. KTU number 2 says, first, identify the means to be compared and the test type. Next, select a significance level alpha, and then collect a sample or samples of data. Key number 3 says, then use the sample data to calculate some descriptive statistics, NT, and the degrees of freedom, df. Key to understanding number 4 says, then use the appropriate t distribution and alpha to determine t critical. KTU number 5 says, or use the appropriate t distribution and t to determine p. The 6th and final key to understanding says, if t is greater than or equal to t critical, or equivalently, if p is less than or equal to alpha, then there is a statistically significant difference between the means. Otherwise, there is not a statistically significant difference. And here, on one page, are all 6 keys to understanding the concepts in t-tests Part 2. You may wish to pause the video at this point and read them all together. Okay, now let's take a closer look at each key to understanding. KTU number 1 says, much the same thing happens in the 3 types of t-tests covered in Part 1. There are just different formulas for t and for the degrees of freedom, df. T is the test statistic for the t-tests. There is a video as well as an article in the book about t, the test statistic and its distributions. It says, t is a measure of how likely it is that a difference in means is statistically significant. Like all test statistics, t is calculated from sample data. Here is a descriptive formula. T equals the difference between the 2 means divided by the standard error. This description applies to all the t-tests. But each test has different formulas for the mean, for the standard error, and for the degrees of freedom, as we'll show in the next slide. For each of the 3 types of t-test, here are the formulas for calculating the difference between the means, and for the standard error, and for the degrees of freedom. But you don't have to really understand or memorize these formulas. Spreadsheets or statistical software can do all these calculations for you. You just select the t-test and provide the data and a value for alpha, the level of significance. However, you may find these formulas useful in getting a conceptual understanding of what's going on in the tests. Each of the three types of t-tests compares two means, but the two means are of different types for the different tests. This is explained in the Part 1 video. So the mathematical formula for the numerator is different for each type of t-test. Likewise, the mathematical formula for the denominator, the standard error, is different for each type of t-test. And finally, each type of t-test has a different formula for the degrees of freedom, df. df is not involved in the formula for t. However, there is a different t distribution for each different value of degrees of freedom, and different distributions give different values for the probability of a given value of t. KTU number 2 says, first identify the means to be compared and the test type. Next, select a significance level, alpha, and then collect a sample or samples of data. These three steps are shown as steps A, B, and C in the table. This is the usual sequence in inferential statistical analysis. The order is important. We'll go through them in sequence. Step A in the table. Identify the means to be compared and the test type. One will determine the other. See the Part 1 video. If hypothesis testing is to be used, a null hypothesis must be stated at this time. The question or problem to be resolved by the test is stated in the negative. Step B. Select a significance level, alpha. As noted in the video on alpha, in order to keep the integrity of any test, we must select a value of alpha, which is the level of significance, before collecting a sample of data. The level of confidence is 1 minus alpha. So if we want to be 95% confident in our conclusions, we select alpha equals 5%, 0.05. This is our clip level for the statistical significance mentioned in the null hypothesis examples. Step C is to collect the sample or samples of data. Key to understanding number 3 says, then use the sample data to calculate some descriptive statistics as well as t and the degrees of freedom df. In step D, the descriptive statistics are calculated or derived from the sample of data. We get the sample mean, x bar, the sample standard deviation, s, the sample size is n, and the degrees of freedom df. This output from step D becomes the input for steps E and F. In step E, for the one sample t-test, we specify an estimate or target mean for the population or process. For the other two types of tests, we calculate the value of t using the formula appropriate to the type of t-test. In step F, the degrees of freedom is determined and we use it to identify the appropriate t distribution. KTU number 4 tells us to use the appropriate t distribution and alpha to determine t critical. This is step G in the process. Given the t distribution and the information on whether it's a one-tailed or two-tailed analysis, the test uses the cumulative probability alpha to calculate the numerical value t critical. Critical values of t are available in tables or they can be calculated with spreadsheets or software. T critical and alpha convey the same information, and either one can be derived from the other along with the t distribution. A t distribution is a probability distribution pictured as in these curves. The horizontal axis is for the values of t. The height of the curve over a given value of t is the probability of that value. Of more interest is the cumulative probability of a range or ranges of values of t, because alpha and p are cumulative probabilities. A cumulative probability is calculated as the area under the curve of the range of t values. Let's say we have selected a equals 5%. So we shade 5% of the area under the curves below. For a one-tailed, right-tailed, or left-tailed test, we shade either the rightmost or leftmost 5% under the curve. In the t distributions pictured, t critical is calculated as the value of t, which defines the boundary of the shaded area under the curve representing alpha. There are two types of one-tailed t-tests. This shows a right-tailed test. It would be used to answer the question, have our school's test scores shown a statistically significant better performance than the national average? A left-tailed test would be used to answer the question, does our new process show a statistically significant lowering in our defect rate? And we'd use a two-tailed test for this type of question. Has there been a statistically significant change in either direction from the historical process mean? For a two-tailed test, alpha is split in half and the halves are positioned under the left and right tails of the curve. The t-distribution is symmetrical about its mean of 0. T-critical is the distance from the boundary of a shaded alpha area to 0. For a two-tailed test, the half alpha areas are smaller than the full alpha area. So they would begin farther out from the center. So the boundaries marked by t-critical and its negative will be farther from the center. That means the absolute value of t-critical for a two-tailed test will be larger than that for a one-tailed test. Key number 5 says, or use the appropriate t-distribution and t to determine p. If we're going to make a yes or no conclusion, that is, the difference is or is not statistically significant, then step G and step H are redundant. Comparing t to t-critical gives us exactly the same answer as comparing p to alpha. However, as explained in the video on p, the p-value, some testers are not looking for a yes or no answer. Instead, they use the p-value to define different gradations of how strong the evidence is against the null hypothesis. For example, p less than 0.05 may be considered moderate evidence against, while p less than 0.01 could be considered strong evidence. The situation with p and t is kind of the reverse of the situation with alpha and t-critical. To find the value of p, we start with the value of t, which forms the boundary for an area under the curve of the appropriate t-distribution. P then is the cumulative probability of the area under the curve along a tail which is bounded by t. P is the probability of an alpha error. An alpha error is also known as a type 1 error or a false positive error. It is the probability that the test will falsely conclude that there is a statistically significant difference between the two means, when in fact there is not a statistically significant difference. Like alpha and t-critical, t and p convey the same information. If you know the value of one and which t-distribution to use, you can calculate the value of the other. KTU number 6 says, if t is greater than or equal to critical, or if p is less than or equal to alpha, and these two comparisons are statistically the same, then there is a statistically significant difference between the means. Otherwise, there is not. The shaded area representing alpha is sometimes called the rejection region. If t is in this region, as in the left graph, then the null hypothesis is rejected. Conversely, the unshaded area outside alpha, which is 1 minus alpha, is called the acceptance region. If t is in this area, as it is in the right graph, we fail to reject the null hypothesis. We said earlier that t is a measure of how likely it is that a difference in means is statistically significant. So the larger value of t, the more likely it is that the difference is statistically significant, and that we reject the null hypothesis. Now, what factors make t larger? Let's look at the generic formula for t. T equals the difference between two means divided by the standard error. So a larger difference between the two means and or a smaller standard error would make t larger. The generic formula for standard error is standard error equals the sample standard deviation s divided by the square root of the sample size n. This gives us t equals the difference between two means times the square root of sample size divided by the standard deviation. So the following three things will make t larger: a larger difference in the means, a larger sample size, or less variation in the sample data. And if t is large enough, that is, if t is greater than or equal to t critical, then we conclude that there is a statistically significant difference. That is, we reject the null hypothesis. Alpha is the shaded area in these diagrams, and P is the hatched area. In the left diagram, T is greater than T critical. So P, which is the hatched area under the curve to the right of T, is less than alpha, which is the shaded area under the curve to the right of T critical. And the conclusion we draw from the test is that there is a statistically significant difference in the means in the t-test. The right diagram shows the opposite situation. T critical is greater than T. So P, which is the hatched area under the curve bounded by T, is larger than alpha, which is the shaded area under the curve bounded by T critical. And the conclusion of the test is that there is not a statistically significant difference between the two means. Hypothesis testing and confidence intervals are the two major methods of inferential statistics. Instead of comparing P to alpha, or T to T critical, as in hypothesis testing, it is logically and statistically equivalent to use confidence intervals. These are provided by the software used in t-tests. Confidence intervals are in units of the data, x, not in units of t. See my two videos on confidence intervals for more on that subject. This has been the second video in a playlist on statistical tests. Next are videos on the 3 chi-square tests and one on nonparametric tests. You can always check the videos page on my website for the latest status of videos completed and planned. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book if folks like you tell me that more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a statistics tip of the week series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page Statistics from A to Z and on Twitter as @StatsA to Z.